Hello and welcome to yet another interesting conversation about software development. Only today I have a very special guest who is a scientist who studies computer programming and how programmers think and how we can develop things better. And I'm looking forward to this conversation because I've been fascinated by science for a very young age, but there are still some challenges in bringing science to software development. So it's very interesting to see this. So I'd like to welcome Felina Hermans.
Thank you. Really nice to be on the show today.
Before we start, so a quick story on how we actually got in touch. Many years ago, I wrote a tweet that I was looking for people in science to collaborate to, and you are the only one who answered.
Yeah, that sounds like something I would do. I'm always trying to collaborate with people outside of academia.
Yeah, that was really nice. And then I think we invited you to a few conferences. I am still unhappy about one thing that I did at one of the conferences. I didn't know how to pronounce your name, so I apologize for a very long.
Yeah, that's okay. This goes wrong often.
Yeah. Okay, so first of all, it would be interesting, and what I ask from all our guests is to give us a short bio, and in particular for you, I think what's interesting is what made you go into science and into academia?
Yeah, so that's a great question. I've actually wondered myself as well. How did I end up here? I think when I was young, like when I was in high school and early university, somehow I learned that a PhD degree was the highest degree there was. And I considered myself very smart as a kid. So then already I thought, oh, I want to have this PhD degree because it's the highest degree that I can achieve. So then this is something that I want. So I think I wanted to have the PhD as the highest degree, even before I knew what it even was and what science was. But then when I started to actually do science as an undergrad, my first research project, I actually really liked it. And some professors also in university encouraged me to explore this further, especially to explore the human factor of computer science that I was already interested in when I was earlier in my studies. And then once I started to understand what a research career is, just to find a really hard problem and then sink your teeth into it and continue until you find a solution. Yeah, then I turned out that I really actually liked doing science. So after my PhD, I stuck around.
Yeah, that is, I can imagine this is very interesting. I've been reading about science a lot, but not actually practicing it. And one thing I learned from interacting with you over the years is that it's very hard to define experiments, right? I think that's one of the hardest parts, and to separate variables and all those things. Is that like the most difficult problem in science that you see in your activity, or?
There's so many different parts of science that are really hard. So if you take the whole trajectory from, let's say, an idea to a result, then there are many things that are very hard. So solving the right problems is also very hard. And that's a totally different kind of hard from setting up an experiment, right? What are the hard problems to solve? And I think also that is specifically a reason that for an academic, I go out a lot. So I go to, not now because of Corona, but otherwise, I go to many developers conferences and I chat with developers and I interview them for my podcast, because you can be excellent in solving the wrong problems and then you still haven't changed anything, right? So the first step might be really to nail down what is a problem. And sometimes I think in software engineering and computer science, maybe we're focusing our energy on the wrong problems. I mean, if you think of typical things that we discuss, like what programming language to use, tabs or spaces, Vim or Emacs, developing on the Mac or on a Linux machine or on the Windows machine. These are things that we spend our time on, and maybe they're not the most important things. And I like it that the last 10, 15 years is something probably also you have actively worked on. We've gone from more technical issues as a field, I think, more and more towards issues of communication, language, DDB, issues of design, issues of human factor. So yeah, I think I would say if I was really pressed for what is the hardest problem, I think the hardest problem is knowing what the problem is. Because once you know what the problem is and you've convinced other people in your surroundings that indeed this is a hard problem, then yeah, I will not say solving the problem is easy, but at least you are spending your energy in the right place. And that's also something that will be sustainable, that will keep you going. And for example, when I tell people that now I'm working on programming for children, then people say, oh, that's so valuable and programming is so hard to learn. And I want my children to also be excited about this. So if you find a topic that energizes others and you keep convincing yourself that it's something that is worthwhile to work on, then solving it will happen because you can continue to put your energy there.
Yeah, and I can relate to that because often even in programming, I know a lot of technical people who have decided to build a product, and they realized that they were very focused on building the product right and correctly and with the best architecture and design and so on, but forgot about actually solving a real problem for users. And then of course you have a beautiful code, but it doesn't serve anyone. So it sounds very similar to this. So, and I see a lot of connections here because often when we are building new products, I think something that most programmers don't realize is that we are in the unknown. We don't actually know what will work, what doesn't work, and so on. And so even here we need a more an approach that's closer to science, with hypotheses, with experiments, and so on. And it's not that easy to do for programmers. And I would think also for when you try to use a new technology or something you've never used before, it's still, experiments and something like this help a lot.
Yeah.
So, okay, we have, now I've mentioned that we have some challenges with using science in software development. And I think one of the most common challenges is that developers as a group are not trusting the science results in this area. It always seems like it's something different, or we have a domain where somehow it's in a void and nothing else applies to it. So what do you think about this?
Yeah, so that's a very multifaceted problem. So I'll try to pick apart some of the reasons for this, and then we can address the reasons. So I think one of the issues is that if you go to a computer science program in university, typically your computer science program will be part of STEM, of science, technology, engineering, and math. So very much the hard natural sciences. And those sciences have a certain way of doing research. So if you think of physics, physics is really, you have a hypothesis, there's gravity, this is a pen, if I drop it, it will fall. I can measure how quickly it falls. That is a way of doing research. There are also other ways of doing research. So if we say science, and not just only for computer science education, but also in general in society, if we say science, we often mean the natural sciences. So that means that there is something precise to measure. You can measure how quickly this falls with how many decimals you want. That is a possibility. And if you try to transform that type of science and then apply it on computer science, it's sort of hard to do because there are so many human factors. People aren't things that you can draw. And it's really hard to do an experiment. So many people are looking for maybe the wrong type of science or the wrong type of certainty. Because if you would do an experiment in computer science, of course, they are done and they definitely have their value, but it's really, really hard to do because either you would say, imagine you want to know what's the best way to approach a project. You would have to say, okay, we do this project twice. You have group A and group B, and then for 9 months, they work on the project and they get the same budget and the same computers, and then we see what happens, which is really nice, but of course, very, very expensive and sort of unrealistic. So then what you get as an alternative, what scientists do is a smaller project. Very often they do stuff with students because they are free or cheap and available. So then it's, instead of having 2 teams of professionals, having 2 teams of students that are smaller, or rather than a year-long project, you have a project that's a few weeks, you can still learn something from that. However, that then, of course, it gets easier for professionals to say, oh, but yeah, these were undergrad, or oh yeah, but this was just a 5-week project. So the criticism, it's fair criticism, but it's easier to criticize because it's harder to do experiments. So to come back to these different forms of doing research, there are other ways of doing research that also very much add value. So the question is really, what is the research question? So if you want to know which method is better, then maybe an experiment is the best way to go. But maybe you're also interested in what type of things are discussed in meetings. So I know this amazing paper where there were a bunch of researchers that for a few months just sat into Scrum stand-up meetings. They just sat there, didn't participate in the meeting, only made notes for a few months. And then they said, hey, after a few months, hey, people in the team, these are the things that you typically talk about. And this is more or less how much time you spent on all the topics. And then the team was like, wow, we didn't know we spent so much time talking about such and such. We thought that this was more important. So of course, from people's behavior, you can also see what they find important. And that too is science. And that too is a scientific method that what we would call the qualitative research, where you're more trying to understand than to measure. And I think that's also a really valuable way of knowing things. And I always tell students, because my students, my undergrads also want to rush into experiments. They want to say, oh, I want to know what's the best programming language for teaching, right? And they would want to have one undergrad program in Java and one in Python, which is equally unrealistic as doing a whole software project twice. And then I say, okay, so what are your variables? And they're like, yeah, what is best? Okay, so what is best? You know, that's already a hard question. But what are you optimizing for? Do you want to minimize dropout? Do you want to maximize grades? Maybe you want to maximize inclusivity. You want to have not too many women or students of color drop out. That might matter to you. Maybe you care about how likely students after the course are to say, oh, I would like another programming course, which isn't the same as getting good grades. I mean, an easy way to get good grades is to give everyone an A. It's really easy. It's not very hard. So maybe you're interested in other things. And then if you start to question, what is the thing I'm interested in? Maybe there also interviews or observation studies could really help, because maybe you want to ask students at the end of a course, what do you like best and what do you like most? From that, you can then gain an idea of what variables you want to test, and maybe then you want to do an experiment. So all the way coming back to your question, I think one reason that professionals don't take all our studies serious is that they're looking for the wrong kind of science. They want to have experiments. They want to know what is best. But then if you press on, they don't even know what they want to know best. And secondly, because experiments are hard, because building programs is hard, and you want to have realistic examples, we tend to have smaller sample size, and that also makes people suspicious, even though the results might still, of course, for very small sample sizes, might still be very true, but then criticism is easy.
Mm-hmm. Yeah, I can see all that, and I have a few examples that I keep seeing. There are many studies on the effectiveness of test-driven development again and again and again, and it's interesting that I can relate to them when I look at beginner programmers, but if I would look at people who have been practiced, for example, test-driven development for many years, it's like it's a completely different world. And so I always keep asking this. I have this question in my mind of, is it better to look at people who are experts and try to learn from them, or is it better to look at people who are beginners and try to see what their challenges are? And I guess this is already a complex question, but it shows one of the challenges.
Two different questions, and there's a thing called the expertise reversal effect, which means that what benefits beginners does not benefit experts, and the other way around. So it might very well be, if you're talking about trade-offs in designing a programming language or designing a library or a module, it might be that something you put in to help a beginner is ultimately harming maybe the productivity of an expert, but something you put in to help an expert to make them, extra productive, to make the language extra powerful, might harm understandability or learnability for a beginner. So yeah, it could be two different questions with two different outcomes. It's really a bit like training wheels on a bike are very useful if you're 5, but then if you're 10 and you want to go really quickly and you want to take the turns like this, then the wheels on the side are going to harm your ability to go really fast. So that's probably similar for programming language.
Yeah, in general, for these programming techniques, it seems to be very hard to actually do a study, and indeed, I have an issue with I criticize them for using students. On the other hand, it has been very interesting to me. For example, with test-driven development, I did some experiments just by happenstance with people who knew nothing about programming languages and were just trying to learn a programming language. And so what I would do is I would write a simple test for them. Well, start on a problem, write a simple test, and then say, okay, so now write whatever code you think might solve this test, might make it pass. And they would write, and then we would discuss the differences in syntax between what they would expect and what's really in the program. And then I would write the next test and so on and so forth. And this came very naturally as a learning method. But for some reason, it's not natural for programmers who have been trained differently. So there seems to be a switch there.
Yeah, that's probably that reversal effect where things that work for beginners can harm experts.
Yeah. So you have been doing some research in how people learn programming languages and also in Excel. Can you tell us a bit more about your research? Because it's quite interesting.
Yeah, so most recently I've indeed been really, really interested in the psychology of programming. What happens in your brain if you program? Because if we understand that, then we can use that understanding to improve programming languages, to improve code bases. So that's the most recent thing I've worked on. And I would say it really follows or builds upon all the work I've done in the previous decade. Where of course initially I worked on code smells and refactoring in spreadsheets. Code smells and refactorings, or let's go with code smells. Code smells are also an issue because they're confusing, right? Mm-hmm. So if you have a method that has a very, very long parameter list, many parameters, the problem is you cannot remember all the parameters. Or if you have a very long method, then it gets really hard to really comprehend everything that's going on. And Fowler in his book doesn't really talk about the cognitive effects of code smells, but once you know a little bit more about psychology, then you see that many of the code smells as they are defined actually refer to or build upon the limitations of the human mind. And we know that human short-term memory, you can more or less remember, we used to say 7 plus or minus 2, so between 5 and 9 items at once. That's the most that you can remember. And newer research even says that it might be lower, that it might be between 2 and 6. So people can remember more or less between 2 and 6 things. So then going back to the long parameter list, if there are more than 6 parameters on your method, people are not going to be able to remember all 6 at the time. So they might see the function call and they're like, oh, 5, 7, 3, all the numbers. And then you go to where the function is defined because you want to see what actually is the meaning of this thing. And then you've forgotten the values, or the other way around, you go to the function definition, you read, angle, power, speed, or something if you're controlling a motor. And then you go to your function call and then you've forgotten the meaning because you can only remember these more or less 2 to 6 things. So code smells are very related to how the brain works. And if you know that, so you can just memorize, let's not use too much parameter because, Fowler says so, and it's a great idea. But this deeper understanding of why things are confusing, that's really, really interesting to explore. That's also what I'm exploring in my upcoming book, which is exactly this idea of how do brains process things, how do brains process programming, and how can we use that knowledge to make programs easier to read and to write better programs.
Yeah, and I remember learning about, I've read 1.5 chapters from your book since you sent them to me, and I only managed to read a bit, but it was very interesting to see the concepts of that I was already familiar with, of working memory and short-term and long-term memory, and indeed it makes a lot of sense to see how they interplay with reading code. Do you think that this is also related to linguistics and how we write or read text in general?
Yes, yeah, I definitely think that. So another thing I've been working on, so this is maybe turning into a Felina commercial, but all the stuff I'm selling is more or less free. So something I recently worked on is a new programming language for programming education called Hedy, hedycode.com. And Hedy really takes the idea of learning a language, a natural language, to learning programming. Because if you're learning language as a kid, if you are a 5-year-old or a 6-year-old, then we do not give you all the grammar rules at once. We're already happy if you're a 6-year-old. We're happy if you can just do letters, right? Not even capital letters, just like small letters, and then no interpunction, no periods and no commas, not even sentences. You just start with words. And then we do sentences. And after a while, then we say, okay, from now on, every first letter is a capital letter. Okay. The kid gets that new rule. They practice the new rule. And then you say, hey, you know what? You can end a sentence in a period. That's the end of the sentence. And then a new sentence can follow on the same line. So for a 7-year-old, that's like, at first the concept of a sentence and a line, it's the same thing. And then it splits out to become different things because of syntax. You add the syntax. So that's the exact idea that we also take in our programming language, Hedy, is we start sort of syntax free. You can just say print and then any word you want, and it's just printed. So you don't need brackets, you don't need quotation marks. You can just say print and then all the words follow. And then of course, like not having periods, that does limit you in a way, because if you don't have periods, you can only make very short sentences. And if you can only print words, then for example, you cannot print the word print because that's already a keyword. So you run into limitations. That's okay, because then at the next level, with a gradual programming language, at the next level, we add this little bit of syntax to solve your immediate problem. Like, oh, now you cannot print the word print. Now let's do this. And then you can print multiple lines and all the stuff that you unlock once you have brackets and quotation marks. So I definitely think that how people learn a natural language is a great guidance for how people learn programming. This is also, again, one of the things that I cover in my book. In learning languages, it's very common to use something called flashcards, which is like a card, and then on one side of the card you put the French word, and then on the other side of the card you put the Dutch word, and then you can practice by looking at the cards. A little bit like Duolingo also does, where you have a description in one language and you translate it to a description in another language. We know that's a really, really good way to strengthen your long-term memory. And then if we translate that to programming, which I sometimes try with students, they're a little bit reluctant. I give them flashcards with like a for loop on the one side in Python, and on the other side it says for loop, and then they have to write the for loop that's on the other side of the card. And they're like, but I could just Google all the syntax. Why do I need to memorize this? And then you try to, you align this with a natural language. We also say, yes, if you want to write a letter in French, you can first write it in Dutch, and you can look up every word in the dictionary. That's a thing you can do. But it takes a very, very long time, and you will probably never write really great, creative French poetry. If you are translating word by word, you will not have the speed, but also you'll not be immersed in the culture. You could only make Dutch-like sentences translated to French. You can never really make Frenchy French sentences. So if you take this perspective of learning a language, then it also makes sense that, yeah, you do have to memorize some syntax, because it's just not efficient, even though it's possible, to look up the syntax of a for loop or an if statement all the time. You can do it. Like you could translate every word in a French letter. It's just not going to be efficient, and you'll never really be a fluent Pythonista.
Yeah, it's interesting to hear this problem since I have a very different experience. I learned programming because I enjoyed it and I spent a lot of time playing with the syntax and trying out different things. So I never feel the need to search for the syntax unless I'm working on a completely new programming language that I haven't seen before, like completely different. You have examples in your book of APL, which is one of those languages that I have no idea how to write.
Yeah, that's also the reason we put it in the book, because if you're an expert programmer, many programming languages look a bit like each other. So it's hard to confuse professionals with a piece of Java, even though they've never seen Java before. So I rely on APL as a language to help experienced developers again experience how it is to be a beginner, how it is to be someone that has no clue what everything means. So APL is structured in such a way that it helps me to confuse people.
There is one thing though that I've been very interested in linguistics and in how people learn languages because well, my mother is a French teacher and we've been discussing this for a long time, and then I was very good at grammar in high school, and then it turned out it was Chomsky's structured grammar, which is also applied for compilers. So there were some connections there, and one thing that I have learned from what I listened to and read is that it seems that listening to something is easy, but actually learning to write is something that's much more difficult. Learning to read is easier, learning to write, and especially to write in a way that is, let's say, good or easy for other people to understand, it's much more difficult. And this seems to be the case for programming as well. Do you think about this when you design learnability into a programming language?
Well, actually, it might be the other way for programming. So there was this recent paper. This wasn't my paper, but this was a paper by someone else, very recent. So this occurred in 2020, and it's called "If They Build It, Will They Understand?" And they look at Scratch programs that children created. So they look at a kid that's made a program that contains a for loop and contains a while loop or contains a condition, and then they take a little test with these kids, like, hey, here's a condition. Can you explain what this means in words, or can you predict what this program does? And they actually found that it's very possible that children can write programs without being able to read the same program. And we're actually now replicating that study here with students, undergrads in the university, where we find the exact same thing. So they manage to hand in homework that has a for loop and an if statement, and then we give them a similar program and we ask them, explain this in your own words. And then they're struggling, or they're sloppy, or they're confused. So it might be the case for programming that students can write something, but they can't really read it, probably because they do rely on Google Stack Overflow. They might rely on what their neighbor is doing, and they might also rely on trying out example code, because if you only learn the for loop and an if statement, if that's the only thing you've seen after 3 or 4 weeks, the solution is going to be a combination of those two things. You just know it's either an if statement that has a for loop in it, or it's a for loop that has an if statement in it. So just by trying out the limited options that you have, if you don't have lots of syntax knowledge, you will probably get it. But that might not mean that you really truly understand what's going on. So some people, Benji Chi is an example at the University of Washington, is and I agree with that, is advocating for a read first pedagogy in computer science, where rather than saying, hey, this is a for loop and now reverse a list or something, say, hey, this is code that has a for loop, let's read it together. What happens in the first line? Oh, what happens in the second line? This is what happens. You can make a little state table also with all the variables involved. Oh, now this variable is 0. Oh, this variable is 1. Just a basic example where we see students struggle to really grasp the notion that if you have something like for I in range 5, this I is a variable. It first has the value 0, and then it has the value 1, and then it has the value 2. Even though they might be able to, by just smashing the keyboard, finally get a program running that prints 1, 2, 3, 4, they might not understand why it does that. So that's my hypothesis, and the hypothesis of a few other people in programming is that maybe this focus on having people write lots of code without being able to read it first, it might be a step too far.
Well, that's interesting, because it actually relates to things that I've seen in production with professional programmers who are writing code today, but 1 week later, no idea was there. So it seems to be something that's prevalent. It also reminds me of a conversation that I had with Rebecca Worsbrook, who's a very experienced programmer. And I was basically repeating the mantra of, code is more read than written. And she was like, no, people play with code more than they read or write it. So perhaps this is one of the reasons why you actually get this effect, that you can actually play with code around, run it, write something or copy paste something and then see if it works or not. And
yeah, I also think it very much has to do with what you've practiced. So running code is what we practice. Putting a breakpoint somewhere, running the code, putting print statements or console logs. This is something from if you go to university or a boot camp, or even if you're entirely self-taught, that is a practice you are taught. You are practiced. You're told also, oh, if you're confused, put a print statement in. That's what we tell students. If you're confused, friends, put in a print statement. So because this is what we tell people is the way out of confusion, yeah, that's what they're going to do. I mean, how often do you practice reading code? And what strategies do you know for reading code? When I sat down myself and I thought, okay, I have to read some code. I have to really understand it. What do I do? Yeah, run it. That's our go-to strategy, right? Because we don't practice other things. So in my book, I have a few other things that you could also try that might also work in addition to running the code. For example, trying to summarize the code is a really good way to also get a grasp. Just look at the code, read it in peace, and try to write a one-line summary. It might be wrong, but then you have a really clear written down hypothesis. And if you run the code then, it's way easier to check what it's doing, or identifying what is the main concept in this code. Something, we have some small finger exercises as well. Simply just circle all the variables and draw lines between what variables are called where. Just to gain a sense of what's going on here. It's not surprising that people will grab the one, they have a tiny toolbox with one tool in it, and the tool is hit the play button. So sure, yeah, that's what they're going to do, because we've never been taught other ways of understanding code than running it and putting print statements all over the place.
On the other hand, that one of my, I noticed that whenever I have to go to a client and start helping them with existing code, which they don't even understand anymore, and I have no chance of understanding, the worst thing I can do is to start reading it, because that will take like days and days of understanding. And it's actually this idea of experimenting with code, so starting by writing a few small tests and see how the system reacts to you and so on. It also seems a valid engineering approach in discovering, something that you don't actually know. Yeah.
Yeah, it's definitely not a case that I say, oh, never run code. The only thing you want to do is print everything out and staple it together and read it like a book. But it's often a good idea to just have a variety of tools at your disposal. And yeah, it might take a long time to read code, but it might also take a long time to run code. And it is what you probably want to do is indeed write a few tests, and then it breaks somewhere, and then you have maybe one class or one object or one instance, one part of the code base where you're like, okay, so it seems this is central. And then maybe you do want to say, okay, so this seems to be a very important part or something You have lots of code metrics, of course. You can easily measure what class has the most churn, what's changed the most, or what's changed by the most people. So once you've identified a piece of code, we're like, okay, it's probably going to make my life a lot easier if I understand this. Then it might be a good idea to, rather than running that code, try to write a summary or try to highlight what are the important things. And this is also very much something that you can do in collaboration. I've been running code clubs within companies with professionals, which is really, really nice, where we take a piece of code, and this can be something random we grab from GitHub or something from their own code base. We sit down and we do a round with all the developers in the team. We say, okay, what's the 5 most important lines? And that opens a discussion because, of course, they don't agree. So some people say, well, importing the libraries is the most important because, without the libraries, it wouldn't run. And other people say, oh, these lines are the most complicated. But that's why they are the most important. Or these are hooks where other functions, other classes call this code. So just that discussion of reading something collaboratively and together forming one mental model of what the code is doing, we've also found that exercise of reading code together is very, very valuable and also slightly easier. Running code together is harder. Reading code together, a little bit like critical reading of a text, where you really exchange perspectives, is not only important because you're reading code together, but also because you are gaining a better understanding of different perspectives on the same code.
Yeah, that sounds very interesting. And this leads me to another thing, which so we both know Peter Hilton and his work on visualizing code. And I feel like the tools that we have are very limited at actually visualizing, annotating, and doing this kind of reading. And I know that I am familiar with Tufte's work on how to create, how to design books so that you can actually learn from them and understand them. Perhaps there's also a tooling problem. Do you think so? Or?
Yes, definitely. So for various reasons, the idea of projectional editing never really, caught on. So programmers really like to edit text rather than edit other forms, like more structural. For like something like Scratch is actually, maybe Scratch is the most successful structure editor, where rather than changing syntax, you are changing blocks of syntax. But the idea of projectional editing has sort of two sides. And I think because people like to edit text, the editing the structure never really caught on. But another idea of projectional editing is that you can project different views on the code. So there's been some experiments, actually. There was a really cool tool called Code Bubbles, which tried to break away from code is in a file and had a different view where you would have one function or method, and then if it would call another method, then like bubbles, the method would be next to each other, and then the next method again would be next to each other. And for a while, this is maybe 10 years ago, for a while I thought, oh, that's so great, and I'm sure that's going to catch on. I think there was even a Visual Studio plugin at one point, but then it sort of died. I don't really know why. I must say, I also tried it for a while, and I found it really hard to break away from having my mental model of code is in a file, especially if you have a code base on which you've worked for a very long time. People tend to have a very strong spatial memory. So if you're looking for something in a book, you might very much remember, oh, it was on the top of a left page, because we have a good memory for where things are. So similarly, people tend to have a good mental sense, a physical, spatial sense of where things are in a file. So breaking away from that, maybe I didn't have enough stamina. Maybe, I should have tried for a longer time. But I guess this is the issue. I don't know what the issue is, but this different view of code bubbles never really caught on. So I think it's hard. Apparently, it's hard to break away from how we're used to looking at things. So there's definitely a market for tools, but circling back to the beginning of the interview, what problem are we actually solving? So what problem would different tools solve? One thing I'm really, really fond of is a framework called Cognitive Dimensions of Notation that describes properties. They're like abilities that programming languages can have. Like it can be, you can have good learnability or consistency. And I really like that framework. And what I like maybe most about that framework is that they describe a number of different programming activities. So if you're programming, you might do different things. So what we call programming is very multifaceted. Maybe sometimes you are searching for information. You are just searching, where is this method called? Or what function do I need to call in this library? Which is really a different activity from incrementing. You already have a code base and you're adding a feature. Those are really different activities. And what the CDM people, the cognitive dimensions of notation people, say from the University of Cambridge is tools might support these activities in different ways. And programming languages might have a different impact on those different activities. So if you're searching, then maybe you want to have lots of redundancy. Maybe it's not, redundancy is not bad if you're searching for information. It's nice if information is all over the place. You can just stumble on the information. So then something like code cloning, it might not be bad if all your methods, all your classes have the same method, then you can easily find it. Whereas of course, if you're incrementing code, then duplication is not great because then you have to make changes to the same method everywhere. So it might be that if you have a better sense of what someone is doing, for example, someone says, oh, now I'm searching, you would get a different view of the code than if you say, okay, but now I'm incrementing. So now, enroll all the duplication into one place and then I can change it. And then you might be able to push it back later. So really reflecting on what you're doing might also improve and help to understand, okay, what's the problem that we're solving here? And then you might be able to make better tools to solve those specific issues. So I love Peter's idea of laying out code like a newspaper with a header and with 2 columns. That's a fantastic idea, but it might still be an idea that's like not in search of a problem, but in search of a more specific type of problem. It might only help with certain code activities and not with all code activities, which I'm just like hypothesizing while I speak now, which might have something to do with why the code bubbles idea never really flew.
Yeah, indeed. I think one thing that I was thinking about is that it might be useful to see when you have parallel flows of execution. So when you have things like if else or for loops and so on, and perhaps see the if and else side by side, kind of things like this, and the for loop was marked in a different way.
Yeah.
Because that is something that I learned to notice in code without actually reading the code, but a tool might actually make it much more obvious, or a view on the code fundamentally.
Yeah, but then again, we go back to the beginner and expert. I guess us experts, we are so used to reading an if top to bottom, right? We just see the condition and we know which branch it will be, and we just read that branch. So I guess if we would be selling something that visualizes an if like this, then soon we would be trending on Reddit or Hacker News, and people would be saying, oh, this is such a ridiculous idea, and you're trying to, make programming available for people that are super not smart. So we maybe drunk too much Kool-Aid, and it might be so very. I totally believe it would be very valuable for beginners. It might even still be very valuable for experts, but now we as experts are used to a certain kind of thing. So the cost of changing to a new way of seeing things is super high, and people might not be willing to pay that. They might resist that kind of change.
This is related though to something else that I've been thinking about, and perhaps you can. I'd like to share this idea and see if you have any opinion. So I've been thinking that one thing I noticed about programmers is we tend to focus a lot on the static structure of the code and forget about the evolution in time or other types of dimensions for the code. And I wonder if this is a function of getting used to the linearity of text, in fact, and not having multiple dimensions in our text fundamentally.
Yeah, so I think that's very true. So one thing, we did a study with children in Scratch, and in Scratch actually you do not have this linearity because you have a 2D canvas on which you can place code. And if you have code that executes in parallel, it can be literally next to each other. So one thing that really surprised us when we tested what do kids understand about code execution is that they did really well on parallelism. Whereas we thought, oh, but parallelism is hard. How come 11-year-olds understand this? Well, we don't exactly know why they understand something, of course, but we could see that they were really good at understanding parallel processing. But then if you look at the code, you're like, yeah, but it is literally parallel. Like the code is literally next to each other. And you can also imagine that we sometimes see this when kids move from Scratch to Java, it's unreasonably hard for them to understand threads because you know what they're used to pasting code next to each other and then it just runs at the same time and then there they go to Java and then we're like, well, you have to start a thread. Why doesn't the machine do this? So I definitely think that the way we lay out code in a linear way is harmful, and not just for parallel execution. I think also for like the call stack. So there's this one file of text, and then what happens also is a graph structure of what calls what. And if you have OOP code base, it's also what inherits from what or what subclasses what. And that graph is entirely invisible. And the only way we make it visible with a debugger is you hop through the linear order of the code. So you're like, oh, here's a function, and then, oh, now we're in the function. We can step into the function. So you still project the graph that is there on the linear thing that is the program. And this now we nicely circling back to my work on spreadsheets. The big problem that we found with spreadsheets is that this dependency graph also in a spreadsheet, especially if you talk about multiple worksheets, is invisible. And then, you know, a big part of my PhD thesis was building a visualization to show people what is related to what, to help relieve that issue of the invisible call stack. And that's still an issue, even though, of course, I know there exist tools where you can feed a code base and then you get a nice PR diagram of all the classes. They do exist. People do use them. But that's, of course, different from really having the view as you have in Scratch. You can really see the things next to each other. So, yeah, I totally agree that there's the linearity of programs and texts and our attachment to storing letters in files instead of graphs in pictures is harmful in a way, even though it might be beneficial in other ways.
Yeah. So for people who are not familiar with the relation between programming and spreadsheets, why is there a relation?
Well, programming is programming and spreadsheets is also programming.
Yeah, I know that Excel is probably the most used programming language by a lot of
That
people.
is what I think. I mean, it has if statements and it has something like a map function where you have data and you have a function and you just take the function and you map it over a list of input values. So yeah, I know it's, although I think it's getting more accepted now to say that spreadsheets are programming. I said it before it was cool.
Yeah. All right. One other thing that I find interesting in general. So there is this idea of teams in software development, particularly agile teams that are self-organized and that borrow a lot from the idea of complex adaptive systems. And on a let's say naive reading of complex adaptive systems, what you understand is they are not governed by many rules. It's like they tend to be, let's say, unpredictable in how they behave, although they have some kind of behavior that evolves in time and can be, let's say, you can try to push towards certain behaviors, but as a whole system. And in this situation, can you actually make studies that and experiments and come up with rules or laws that scientific rules that can be applied?
Yeah, I wouldn't know why not. I mean, you know what's also a very complex adaptive system? The human body, just to give you an example. And yet we can do reliable system. We can do reliable studies of of how medicine prevents or cures diseases. So you have pain in your head, and then you take something in your mouth, and it goes to your stomach, and then your headache is relieved. So that's of course also a very, very complex system, and yet with a combination of, we understand chemistry, we understand biology, physiology, we understand how molecules behave, and from how individual pieces of the system behave, we can make a prediction. And then we do an experiment, and some people get a sugar cube, and other people get actual medicine, and we see, who is healthy and who's still sick. So I wouldn't know why programming is so different. There's also lots of studies on human behavior. Like, we know that if you put something on the bottom of the shelf, then people will show different buying or selling behavior than if you put it somewhere else. If packaging is red, then people tend to have these type of feelings or associations, which are also, of course, complex systems that are influenced by marketing that we see. We're influenced by what other people see. There's so many influences there as well. Yet we can still do reliable experiments in psychology and in economy. So one of the issues might also be, I saw this really nice tweet by Cassidy Williams that was subtweeting another tweet yesterday. So someone said, like, oh, you don't want to have a meeting with programmers. And then they made a little screenshot of a calendar with a meeting, and 2 hours before, oh, I cannot do anything because I have a meeting later, and then the meeting, and then afterwards, coming down from the meeting. And then Cassidy tweeted something like, all professions have this issue with meetings. It isn't that programmers are different. If you're writing your copy editing, you will also be concentrated, and you'll also be like, oh shit, I have to go to a meeting, and then you go back. So programmers like to think that they're somewhat like super special and that no one else in the world behaves like this. But if you have, a marketing agency, there might also be a group of people that collaboratively, without structure, work on something. This is actually sort of getting more and more common in some types of organization, not just programmers. So yeah, I wouldn't know why it would be impossible if we can reliably measure. We can put a little robot on the moon. That's also a very complex system with many features. It wouldn't be, why couldn't we measure how software developers behave in a team? I think it should be possible, even though of course it would be hard, as is medicine and doing these type of experiments in psychology.
But a common, to extend this a bit, every one of our customers tells us that they are different, and that other people, what works in other companies doesn't work for them because their system is different, and so on. And this is very common for consultants. We all know that all customers are different by sharing the same thing, that they think they are different.
Exactly.
But this is a common challenge also to scientific studies. Even if you have a conclusion in science about certain aspects, you will immediately get some people saying, yeah, but this doesn't apply to us because X and Y and Z and whatever. Yeah. Is this a function of, software development being not yet enough research, or is this a function of something else?
Yeah, so I think we're sort of going back to earlier in the interview, but that's totally fine because this is an interesting topic. So it might be like more research is always needed, and sadly there aren't too many people doing software engineering research that are very engaged with companies. So many, like there's this conference, the International Conference on Program Comprehension, ICPC, and they might get 50 papers published in a year of studies that are done with students or with very small groups, or just crawling GitHub and drawing conclusions about that. And they also have an industry track. Maybe the industry track is 2 or 3 papers that have done a study actually in practice. So there's definitely room for more research in practice. Sadly, the incentive system of academia isn't such that you get extra brownie points for doing stuff with companies. Rather the other way around. If you do too much with companies, then other scientists might say, oh, this is just applied research. This isn't so serious. This isn't fundamental. So it's just definitely one reason is that more research could be done and should be done within company settings. That is one reason. But definitely also, I think a reason is that going back to computer scientists are very much part of STEM and science and technology. The way our field is now is that it is filled with many people that think they're really smart and they're smarter than other people. I mean, Elon Musk has just invented a train. It's a train that seats two people and goes like 150 kilometers an hour. In Japan, they've had bullet trains for 50 years that seat hundreds of people. Yet somehow we think, our community at large thinks we are so smart that we can invent and make redundant and any other field because we know it so well, right? So now someone I don't necessarily appreciate very much, Paul Graham of the Y Combinator, it keeps saying, you know, all these fields should be disrupted by programming. Like people in the field don't know how to solve problems. So a part I think of this is also that we celebrate this culture of, yeah, we are the smartest people always, everywhere. So then if scientists publish a study, then programmers with no background in science, who wouldn't know how to do a student t-test or an ANOVA test, you know, they wouldn't know how to do the statistics. And this happens to me because I'm a woman on the internet. People half read my papers, really don't know what it's about, and start sending me all sorts of random criticism about sample sizes and, you know, balancing subgroups. But they don't know what they're talking about. So yeah, of course, I'm open to talking about the results that we found, and this is like certainly also happening to other scientists as well. Fair criticism must be rooted in an understanding of how to perform such a study. And maybe I would almost say, try a study yourself, try an experiment, see how hard it is to find people and to actually do these setups, and then send me an email about how I could improve my work. So I definitely think that that's part of it too, that rather than reading a paper and thinking, oh, what could I take away from this for my daily practice, even though this study, like any study, isn't perfect, because we can never eliminate all confounding factors. It's always, oh, this little thing isn't perfect, so therefore we must reject the whole thing because we are smarter than people that actually know this stuff. I think that's part of it, at least to a certain extent.
Well, I have a theory that programmers suffer from God complex because the way we start to do programming is by absolutely controlling a machine. And we think for many years that we are very good at what we do until we deal with the real life. And then the first connection with feedback is usually very hard and it hits very hard.
And I also think I think you really hit the nail on the head there, that this is also why programmers, I think, tend to gravitate towards solving technical problems, because as long as you stay in the technical problem, if you're trying to optimize this part of C code and you just want it to go 20% quicker, you can make that happen. You can squeeze the processor, you know, to get the 20% out by all sorts of means of caching and all sorts of optimization. You can get it done. It is a very much a scoped problem in which you can retain your gold role. But then once you start talking about very complicated team dynamics and imbalance of power in a code review, then it is less clear. It's less clear what the solution is. It might be less clear what the problem is. And that's not the situation that we're very comfortable with. Again, going back to education, like this is also my fault being a professor. We don't really teach that situation. We don't really educate students for being in a situation in which the problem is super vague, because we always give them these nice little boxed problems and then they solve it and then we say, yes, this was the one correct solution. And then maybe only at the end, maybe of their grad program, when they do a project for a company, is when they're exposed to the mess of the real world, and then still small. And then if they are professional programmers, and they need to still learn a lot about people. So we should maybe also do a better job at preparing students more for people skills and people problems.
Yeah, and I agree. My education, I've also noticed that it's been very hard to switch to solving problems because I wasn't taught how to solve real life problems and how to analyze them, how to split into smaller problems, how to experiment with each small problem, how to find the appropriate technology or solution. Perhaps
Yeah,
not all solutions need to use technology for
yeah.
the different
And
problems.
those are still skills more even within the technical domain. Other things we don't really teach students is how to convince your boss that this is the right design, or
Mm.
how to give feedback in a proper way to maybe a junior colleague in a team. Those are also things we see more and more that they have to learn on the job. And also maybe more than, let's say, 10 years ago, because something like code reviews is really more and more common, where really there's a specific form of communication that's being required of students to be able to do this in a proper way. They cannot say, I read your code and you are stupid. That's just, it's not okay anymore to behave like that. And we have to teach them.
Yeah, and this is one thing that I noticed with programmers that I teach. I had this week learning program with clients on architecture and developers switching to architectural roles. And I always start by telling them a few of the things that they don't know will change. Like uh, now everything is working correctly. When you go to architecture, you have to be prepared that nothing will work correctly. And, computers fail, hard drives fail, you lose files, you don't have backups. Networks fail and all these things, and that's your job as an architect. And then about 50% of the job is communicating your decisions to and negotiating to other people, and that's a very big switch for a programmer, because it go and often people switch into this role without actually knowing what it means. They imagine it's just another technical role where you you step up and you design some diagrams and you send them to developers and everything will go smoothly, but actually it's much more personal leadership. And
Yeah. Yeah, and it sometimes happens, of course, that people with the best technical skills, with the best hard skills, are promoted to such a role for their technical merit, and then they struggle because they have to do things that they're not used to, and they might not even excel in.
to go to another myth about software programmers, do you think there's a myth ongoing that only certain people can do programming? uh, and I'm not talking about groups, because of course the whole thing about only men can do programming, that's whole stupid thing, and I don't want to pay any attention to this. But in general, it seems for many programmers that you have to have some kind of special mental qualities to do this. And I'm curious about uh, if you have any experience in this
Yeah.
area.
So before answering such a question, you might wonder, like, why are we asking this question? So why is this important? Because suppose it would be the case. I don't even know if it's the case. I mean, I have some ideas, but suppose it would be the case. Like, then what? Do we start selecting kids in high school with the right type of mindset, and do we exclude others from being programmers? So I'm not sure I like the way that discussion could even go. So I think it's a topic where you have to take a certain care that if you would be able to decide this, then would you even want to? Because some people, minds aren't fixed, so you might pick
Mhm.
it up later. And then to give you my perspective on this, after this warning, let's go back to language. So do we say some kids just have the brain to learn written language and other kids, they just will never learn? We don't accept that,
Yeah.
right? In at least where I'm from, we say everyone in this country should be able to read at the level of a 12-year-old because it's necessary to read letters from the government. You just have to have this knowledge. And I think programming is getting so increasingly important that we should have this basic level of everyone in this country, in every country, should have an understanding of what a computer is, what you can reasonably expect a computer to be able to do for you. And with language, in elementary school education, we know that the slowest people that are learning to calculate, learning math, the slowest math learner in the room might need 5 times more instruction than the quickest one. But we are willing to pay the price because we think it's important that everyone learns this at a certain level. And I would say to a certain extent, yeah, sure, it's probably true for programming, like for math and like for language, that the slowest programmer might need 5 times more teaching than the quickest programmer. I definitely don't think it's something like 2 types of brains and you can nicely fit people into 2 buckets. Probably it's like everything, like length and athletic ability. It's more or less the bell curve where you have many people that are here and a few people are super quick and some people need a little bit more time. That's more likely. But then I would say, yeah, if some people don't necessarily go really quickly, so they're more of the slow learners of programming. What they need is our patience and our assistance to get a little bit better, so they can get a little bit more towards the middle of the bell curve. What they definitely don't need is us saying, oh, for women and people of color, you're just not made for programming, so you just need a nurse or something, a school teacher or something that doesn't involve any technology. Because also that is no longer true. Any profession, being a nurse, being a school, anything will now involve data and programming. So yeah, that like I'm not fond of that question because I don't like some potential implications. I think it's likely to be something like a bell curve thing. Again, it might relate to this need, this part of our culture where we really want to feel special. So we just really want to we have the mind for it. And it's a small group of people also, and there shouldn't be too many people that could also do this with a little bit more time. Should just be born for it. These arguments sometimes come from a certain group of people.
Yeah, so again, I don't like this question either. It's about it. I believe that you can learn a lot about programming by playing with it, and it can be quite fun, and many people can do this. And then it's up to you what level you want to do, you want to go.
Exactly.
If you are really passionate, or yeah.
With writing, not everyone is Agatha Christie or Stephen King, but everyone can read a letter or write a paper, write a scientific paper. So there's this whole scala of things you can become, and surely not everyone is going to be top of the line, but many people are just solid writers that in their professional lives can write a nice memo or something that adds value to their professional or their personal enjoyment or employment.
To go back to the topic of your book and to what you are saying about meetings and programmers. Another common myth is that if we walk away from the code, it then takes us a long time to load all the information we need so that we can actually get focused and become productive. Is this based in anything, or is just
yeah, that is based on anything. Actually, there's a chapter of my book, but that isn't finished yet, so you don't have it yet. I will send it to you when it's finished.
Perfect.
That is specific interruptions. Although, as I said earlier in the interview, this is probably true for other types of creative work as well. But it's definitely true that if you're programming, part of programming is building a mental model of where is the code, what is referring to what, how is everything aligned and organized. And it's definitely true that you build that, and that if you go to a meeting or you get a phone call or a Slack message, then you might lose your mental model, and it might take you some time to gain the mental model again. Although I would say part of this is also, again, because of our lack of practice of building these mental models. It takes us lots of time because it's something that we don't deliberately practice. And there are definitely ways we know that help. Like people have lots of debates about comments. Should there be comments in code? Should code be self-documenting? But research shows that commenting code actually helps people get back to work after an interruption, and code comments can really support quickly building a mental model. So even if code is self-documenting, code will always be a bunch of lines. It will always be a for loop and an if statement. If it just says, this is Newton-Raphson's algorithm, that's one line, and then I have part of a mental model. Even if the code is really clearly expressing what it's doing, I would still need to puzzle together pieces of the code. So comments can really help quickly get a sense of code, and also practicing to quickly get a sense of code is probably going to make you better at quickly getting a sense of code. So it's true that interruptions are disrupting, but there are ways because interruptions are always going to happen. So there are ways that you can compensate, and there are ways you can practice to get better at it.
I have started to do one thing which is related to this, and that is writing what I call engineering notes, because it's something that all engineers do, fundamentally writing what I was trying to do, where I am, what didn't work, things like that. And this helps me a lot with clarifying my thoughts, and also to going back to the problem at hand later on. So this may be something interesting. But also another thing that I know about cognition is the notion of chunks. So fundamentally, this means when you have multiple things, like, as you said, 5 to 7 things, but they kind of group into one higher level thing, and then you can remember that one easier or make relationships easier. Do you talk about this in the book also?
Yeah, I definitely talk about it, and also talk about how for beginners chunking can be different than for experts. So if we see a for loop, maybe if we even see a for loop that goes like traverses a list in a reverse order, or maybe even 2 lists at the same time in reverse order, and then combines, zips the elements, we can look at that and we can think, oh, that's a for loop that loops over 2 lists at the same time in reverse order. That's like one thing. Whereas for a beginner, this might be 7 or 8 or 9 chunks that might not even fit in their working memory. So that's definitely a part of chunking, in that if you're a beginner, you chunk differently than if you're an expert. This is also being shown by research. And another thing that's important of chunking is that, like I would say everything in life, it has benefits, but it also has downsides. So what we see, what's really, really interesting, is that if you have tiny mistakes in the code, then beginners will see them, because beginners will focus on every letter. So if you have something weird, I once did an experiment in which a line in code was I plus is I plus 1. So that's like super, you would never do that, because either you do I plus is 1 to add 1, or you do I is I plus 1 to add 1. Why would you do I is I plus 1? Because then you're adding I plus 1. So a beginner would really read, oh, I plus is I plus 1. But an expert programmer, they don't see it. They just assume that it says I is I plus 1. So they don't chunk the lines, they just see the whole part of code, or tiny misspellings. There's an interesting example in my book. So you don't notice it because you look at something and you see it at once. So chunking can definitely be a benefit for you to process code quicker. However, it can also trip you up, because, assumption is a source of many errors, and chunking might make you assume that something is there.
Yeah, and I think that's related to black spots and other similar phenomena that we know from cognition that happen.
Yeah, absolutely.
So since I haven't read all the chapters that you sent to me, and you also have a bunch of things more to write, can you tell us a bit more about your book and what other things are in there?
Yeah, so it's going to come out very soon. So maybe if the show is going to be published, and we have a link to the meet, because it's supposed to come out December 2020, almost. So the basic idea is really to teach programmers a little bit about how the brain works. The things you mentioned in the beginning: what is your short-term memory, what is your long-term memory, what is your sensory memory, and what is your working memory. the things you would normally learn in an introductory cognitive science course, but then very much applies to programming. So if we talk about chunking as an example, we look at for loops and while loops and different types of programming elements. And the goal of the book is really to be able to better understand your own confusion and the confusion of junior teammates. The final part of the book is about onboarding, so very much teaching in a professional context. Because very often, if you're confused, you don't really know. So you get this, you go to a new customer and they say, oh, we have this issue with the code. You get the code. And then you're like, wow, this is hard. Why is it hard? Is it hard because this is a programming language you don't know and you don't know the syntax? If that's the case, you need to practice syntax. But it could also be hard because it's very terse. There's lots of, like I said, lots of invisible connections, lots of hidden dependencies. So, you know, this spaghetti code, this function called that function, that's a different type of hard. That's a different type of confusion that you will not be able to fix by learning more about the programming language. You can know everything there is to know about Java, but then you get Java spaghetti code and you're still confused. So there are different reasons that you can be confused. And if you understand that in yourself more deeply, then you can also gain more insight into a solution more deeply. So that's really the goal of the book, is to help people to help people diagnose their own misconceptions, their own ideas about code. And then we introduce a number of theoretical frameworks. Like there's one framework that I specifically really, really like by a Finnish professor called Sayamini. He has a framework called roles of variables. So he says there are just 11 roles that variables can have, and that describes 99% of all programs. So what are roles of variables? This is all informal knowledge that we have, but it's still very helpful to think about. For example, a variable can be a stepper. A variable can be a container that collects something, or a variable can be a most valuable value. So a desired value that you're looking for, like you're looking for the maximum or the minimum or a specific customer. So that's a most wanted value. That is a framework. It sort of makes sense if you read it. You're like, yeah, that's the roles of variables. But you can use that because if you're looking at unfamiliar code, you see these 10 variables. You don't really know what to do. You don't really know what the code is doing. You can take one variable. You can think, okay, what is this guy doing? Oh, well, it starts off with 0. Oh, somewhere in this 7 indented for loop, oh, somewhere 1 is added to the variable. Oh, probably this is a stepper because clearly it might not be called I. It might be called N or M or Z because they were out of letters, right? This is what happens in legacy code. And then you can take another variable. And rather than just looking at the code or stepping through it and thinking, you know, I have no idea what this is doing, having such a framework helps you to chunk code more effectively, because rather than thinking about, oh, this one variable, or thinking about it as a really big class, like it's an integer, you now have this intermediate level of reasoning about code. And then once you see, oh, this is a stepper and this is a container, and this is the most wanted value, then that can help you gain an understanding. So every chapter is sort of a theoretical framework. Secretly, you know, I'm trying to teach a little bit of computer science to people that maybe haven't seen computer science when they were in school, or if they didn't do formal education. So all these frameworks are going to help you to make sense of your confusion around coding quicker and with less effort. That's the goal of the book.
Yeah, that sounds really good, and it relates a lot to what I've noticed. Things like, for example, my Git commits tend to have like 7 types of messages. When I look at a loop, it tends to have about 5 or 6 different rows, different patterns, and so on. And I believe it's much better if we are more conscious of these things rather than use them without realizing.
And also what I found in the coding clubs, the code reading clubs that I've been doing with professionals, is having this shared vocabulary of those things, of those cognitive science concepts, and having this shared vocabulary of the frameworks that we talk about makes it so much easier to talk about code. Because then suddenly you can say, oh, I thought this variable was a stepper. No, it's a container. if you have words and you all agree upon the meaning of those words, then it can be really, really helpful. And you can look at code and you say, oh, the issue here is with my long-term memory because I don't know this part of syntax. Or you could say, oh, the issue is with my working memory because I have to think at many things at the same time. So this vocabulary of a little bit of cognitive science, it's very much like code smells. You know, I love the idea of code smells, not necessarily because I say, oh, you should avoid smells at all costs, but because it gives you a vocabulary. You can say, hey, this is a God class. And someone else that's also seen code smells will understand what that means, rather than saying, oh, this is a very large class. That's what say, no, it's not very large. What makes something large? To have this idea of these are types of code that we want to avoid, it makes it so much easier to have that discussion because you have a shared understanding of what things mean. So I hope that teams that will read my book as a team, maybe as an exercise, read it together, can definitely benefit not just for your own, just getting a little bit better at code reading. That's definitely a valuable skill, but especially in a team where you all know, oh, this person is new, they might lack the right chunks for this code base or for this programming language. It will also maybe make people a little bit more practice a bit more empathy.
Yeah, we can we can definitely hope so. So what is the title of the book and where will people be able to find it? Yeah.
Yeah, the title of the book is The Programmer's Brain, and it's coming out with Manning. And the meat will be released in a few weeks, so that's the first 3 chapters to read online, and it will be coming out somewhere in 2021 in print.
Okay.
But we can definitely link we can link to the meat, and then the meat will also have a link to buying the published book when it's ready.
Perfect. We'll add that to the notes in the section of this video. So before we close, is there anything else that you'd like to tell our audience that we didn't touch upon? And then I have a short question to close.
No, I think we touched upon all the interesting things that I've been working on. So experiments and cognitive science. We talked about the book. We talked about Hedy, the programming language that I'm designing to be more like a natural language. Maybe we can also, in the show notes, link to hedycode.com where people can try it out. It runs in the browser, so you don't need to install anything. That's it, I think. Those are the most exciting things that I'm working on. Just a book and a programming language.
That sounds really good. So I like to ask everybody who's on this show a question about what advice would they give to junior programmers, to programmers who are now perhaps starting their career or are just in the first few years of their career, because it's often useful to think back of your experiences and see if there's anything that can help them.
Yeah, that's a great question. So, I mean, I would say get better at reading code, but that's been covered. So maybe I would say get better at debugging code. So what I see then with students, with novice student programmers, is that very often they want to write code and they just want it to work. Taking the patience to step through code, and the debugger is so powerful. Every time I use a debugger, it's gotten more powerful. You can have like conditional breakpoints that only stop if a certain condition is true. Many IDEs allow you to go back in time. So an error occurs at this line and you can go back up. That's like when I learned to program. Hello, children. When I learned to learn programming, these things didn't exist. We didn't have a debugger, and certainly we didn't have a debugger that could go back in time. So I think the debugger as a tool is something that's powerful. And again, this is on us universities. We don't always teach debugger. I mean, there should be a course on using the debugger. Like there is a course on testing. I think using the debugger is very, very powerful. Just relying on print statements. I know some people prefer this over the debugger, but as I said, the debugger can be so powerful. So I would definitely say to junior programmers, take some code you like that's on GitHub that you can run and step through it. See how the debugger can help you gain an understanding of code, specifically because you will learn how to read code, you will learn how to write code in university, but using the debugger, using the IDE in general, and the debugger especially, is something they probably don't teach you at your university. So that's something you want to get better at, because it will otherwise maybe take you a long time. And it's like it's like a multiplier, because once you know how to use a debugger really well, you can learn unfamiliar code quicker because you can step through it. You can, oh, this is what it does. I can see now because I can go through the code slower. So it will also make your future learning more effective. So I think that would be my best tip, although my whole book is filled with many tips, of course, but this is then my favorite tip.
Yeah, that sounds really good because although people often hear me talking about how I rarely use a debugger because I use tests, but the reality is that when I started as a programmer, I used the debugger a lot and I knew a lot about how to use the debuggers. It was a very useful tool, and now I'm thinking whether it didn't actually help me to understand code back then, so that later on I could actually write these tests and fundamentally store a debugging session into a test.
Yeah. Yeah, so definitely a good strategy once you're done debugging to then add a test. Like once you're done understanding code, it might be really good to add a comment so you don't have to do it again. Once you found a bug or you found an issue, yeah, you do want to add a test. So that's definitely, I wouldn't say those things are different and exclude each other. It's all complementary, and tests and debugging help each other.
Are there any places, and this is the last question, is there any place where interested people can go and read scientific studies about software development?
Yeah, so I would say my website is a very good place. This is www.feline.com. I have blogged about over 400 scientific papers by other people. So I also blog about my own papers, but also hundreds of other people's papers that I've covered on my blog. So I guess that's a good place. I would say something like, oh, just go to Google Scholar and type variable names and read all the papers you like. But many of them are behind paywall, sadly. So it would be nice if more people publish their papers open access. And this is definitely a trend, and scientists are getting better at it. So you can definitely go to Google Scholar, and I would absolutely encourage people to try to just, if they're interested in, what do we know about testing, try to find papers, because more and more papers are not behind the paywall. Very often, if you just take the title of the paper that you can find through Google Scholar and you add PDF to it, you might find a version on the author's website. Many people put semi-legal versions of the papers on their own professional or personal websites. So Google Scholar is definitely a good way to explore research, but sometimes you will find papers that sound super interesting and you have to pay $50, and I totally understand that professionals are not interested in doing that. So alternatively, you might look at my website, which has many of them, and then it links very often to the PDF versions of the papers.
Okay, this has been a bliss. It's been a very interesting conversation. I'd like to thank you a lot for participating, and perhaps we can repeat this in the future once you have more results, or once you publish your book. It will be really great.
Yeah, it was really nice to be on the show. Thanks for the invitation.
And by the way, you can search for Feline and her talks. I think many of them are on YouTube. She has an amazing energy on stage, and it's. I think she's the most energetic technical speaker I've seen at such conferences. So it's really, even if you think you are not interested in this topic, just listening to her talks will probably raise your energy levels. Yeah. Thank you, Felina. It's been great.
You're welcome.
And now to end this, we have to pay our dues to the algorithm. So please like, share, subscribe if you enjoyed this. And until next time, remember to think, design, and work smart.